Okay, lesson 8.8 is the last lesson of this chapter. We're going to be looking at something called improper integrals. And as we can see on the notes here, in defining a definite integral from a to b, where a and b are both real numbers of f of x dx, we dealt with the function defined on the integral from a to b, where f, of course, was continuous on that closed interval. Today we're going to look at infinite discontinuities on that closed interval. You would expect to see vertical asymptotes somewhere in there. And we're also going to consider integration over infinite integrals, going from a real number like 3 or something like that, from a to infinity, or from negative infinity to some real number. Now, at first glance, you might think that it immediately is we're looking at these last two scenarios. If you're integrating towards positive infinity or from negative infinity to a real number, you might expect that your answer would have to be infinity itself. Take a look at this little introduction. As we integrate from 1 to infinity of 1 over x squared, intuition might say, hey, we really have the graph of 1 over x squared, at least in the first quadrant, would look something like so. And we'd say over here is 1. And as we'd continue to find the area bounded by that curve in the x-axis, you might guess that that area, everything is above the x-axis here, would approach infinity. But what we're doing here is say, let's just integrate from 1 to some value t. Of course, what we can do real quickly is realize that x squared is really x to the negative 2. And as we would use our fundamental theorem, we'd bump this power up to the negative 1 power, so we'd get x to the negative 1 divided by negative 1. That would really be equivalent to negative 1 over t. Negative 1 over x, I am so sorry. We can always double check if we found our antiderivative correctly by just taking our derivative itself. Continuing on with our fundamental theorem, you could see that we'd have negative 1 over t minus negative 1 over 1. And this would arrive at, well, negative and a negative make a positive. That's a positive 1. We get negative 1 over t plus 1. But here's the thing. Right now, we've integrated off to some arbitrary real number. What if we really realize that that number can get very, very large? That is, what if we rewrote this problem as the limit as t approaches infinity of negative 1 over t plus 1? Well, we'd know that negative 1 over infinity would be going to 0, and 0 plus 1 would actually equal 1 itself. So this is actually a great indication that integrating on an infinite interval very well might arrive at a finite real number. And we're seeing that right here. Well, just to help us out, we are studying something called the improper integrals. And here's what we must have as we are integrating over infinite integrals. Infinite intervals, I should say. First, f would have to be continuous from a to infinity. And then this is so critical. Really, infinity is a concept. There is no such real number known as infinity. It's just an idea. And really, what we will always do is we're going to rewrite that integral with a limit. We're going to allow t to go to infinity, and we'll make that upper bound be a t. We'll do the problem much the same way we did our introductory problem. And if we arrive at a finite answer, we will say that our integral will converge. We will arrive at a real number. If you don't, you will diverge. Step number 2 is very much the same. You might wonder what's happening as we're integrating from negative infinity to a set number b. Notice this time we again use a limit, but we're going to allow t to approach negative infinity, and we're going to let t be that lower bound. Again, if that limit of that integral winds up existing, the integral itself will exist and converge. And if this limit does not exist, we will say that the integral diverges. So converge means that your limit exists and you arrive at a real number. Diverge means that the limit does not exist. Let's take a real quick look at this problem, integrating from 1 to infinity of 1 over x dx. Well, first things first, let's rewrite this problem as a limit. Make your upper bound in this case be a t, and of course write the limit as t goes to infinity out in front of that. And we'll have 1 over x dx. Now, working this problem out, I hope it's pretty clear that the antiderivative of 1 over x is the natural log of the absolute value of x. However, if you look at this interval, we're going from 1 to infinity. We're always going to have positive values of x. The absolute value truly is no longer needed. We'll use our fundamental theorem to just finish this problem out. We'll say the limit as t approaches infinity of the natural log of t minus the natural log of 1. Now we all know the natural log of 1 is 0. That being said, the limit as t goes to infinity of the natural log of t will equal infinity itself. So really this integral will diverge, or we can say it diverges. So very often that's what we'll be doing, is just indicating, will our integral diverge, and if it converges, make a statement as to what it converges to. Let's take a look at another problem right here. And we've got example 2. And again, we can see rather quickly that we do in fact have an infinite bound down below. What you can do very quickly is rewrite this problem to say the limit as t approaches negative infinity, and we'll integrate from t to 0 of x e to the x dx. Now, of course, working through this integral, you might notice that really what we could do very, very quickly is use tabular integration by parts to help us out. Tabular integration by parts would allow us to find this antiderivative. So we'll let u equal x. The derivative of x would be 1. The derivative of 1 is 0. We'll have e to the x as an antiderivative. dv equals e to the x. Take an antiderivative of it. We'll still get e to the x. Take another antiderivative, and we'll get e to the x yet again. Using this shortcut, we'll have a plus and then a minus. And very quickly, we can see this antiderivative will be x, e to the x, minus e to the x. And now at this point, we're just going to have to evaluate the limit once we use the fundamental theorem, of course. We're going to be plugging in 0 and then subtracting t. So I'm going to keep my limit out in front. And as I plug in a 0, I hope it's clear that we'd get 0 times e to the 0 is 0. But e to the 0 power is a 1. Then I'll say minus, and we'll have t, e to the t, minus e to the t. So this is certainly a more involved problem. Without a doubt, we are not done. We still have to evaluate this limit. And I think what is going to maybe make this problem a little bit more interesting, of course, is the added question about the t, e to the t. We could say this is -1 and then distribute a negative here. A negative times a negative is a plus, so we'd get e to the t. Of course, -1 right here, as t approaches negative infinity, is going to be -1 itself. If we remember the shape of e to the x, we'll realize that as the independent variable is going to be approaching negative infinity, e to the negative infinity will go to 0. The big question, of course, and this is what makes the problem more thought-provoking, is what's happening with t times e to the t. And that, of course, is going to be quite a bit bigger of a question. At first glance, you might say, well, e to the negative infinity is going to 0, and 0 times anything would be 0 also. But we have this other issue that t is approaching negative infinity. So we actually have an indeterminate form of negative infinity times 0. We need to do some side work. And I'm going to do some side work right over here. You might remember we used L'Hopital's rule to help us in such problems. If I have just t e to the t, and we have negative infinity times 0, the big question is, could we somehow perhaps arrive at a nice, simpler form? The big idea, the big goal was to get a fraction. To work quickly, I'm going to bring e to the negative t down. And the reason why I'm doing that is to get a fraction, and then I'd look and I'd see, well, I'd have negative infinity up on top, and down below, e to the negative infinity turns to e to the positive infinity. This would be negative infinity all over positive infinity. I could use L'Hopital's rule. L'Hopital's rule will allow me to see that the derivative of t is 1, and down below I'll have negative e to the negative t. Now, of course, from here, we could even bring that e to the negative t back up if you would like. We could say very quickly that this limit then would be equivalent to a negative e to the t, which would, of course, arrive at 0. So in the end, this limit, this middle section, is going to arrive at 0 also, and we'll have this integral arrive at -1. It does, in fact, converge. So it's going to converge. Taking a look at this next problem, let's just say f is continuous for every x. But look at this next scenario. What if we're integrating from negative infinity to positive infinity? Well, there is a wonderful setup, a wonderful approach that we can do. Pick any real number. They're representing that with the letter a, and integrate from negative infinity to a, and add to that a to positive infinity. By breaking this into two improper integrals, you can now do the problem like we've done earlier. But this problem will be convergent only if both of the improper integrals on the right converge. If even one of them diverges, then the original problem fails and it diverges itself. So if you see that one of those integrals might be divergent, and if it does diverge, you don't even have to check the second one. Well, let's see if we could get a little bit of help here. Evaluate the integral from negative infinity to positive infinity of 1 over 1 plus x squared dx. I'll tell you what, why don't we look at this problem as the integral from negative infinity to 0. Again, just choosing this as a nice simple number to work with. 0 is usually very friendly. And we'll integrate from 0 to infinity of 1 over 1 plus x squared. And let's very quickly set up some limits. I'm going to let the limit as t approach negative infinity be represented here. We'll have our t down below. Here's 0. And we have 1 over 1 plus x squared dx. For our second integral, I'm going to have another limit. I might have another variable represent infinity, like w, and we'll integrate from 0 to w 1 over 1 plus x squared dx.